So all I want to talk about are these few things. It won't take very long, and then everyone can go and eat. So we're still on finite state machines, and the reason I seem to be dragging this out over 2 weeks is because they are so important. And as you'll find with your coursework that you do with Phil Culverhouse, they're kind of central to the timing of everything. Monitoring sequences of inputs and controlling outputs. The subject of state machines is important because it's central to control of sequential logic, serial interfaces, even microprocessors. We looked at Moore machines many times, and we've always deferred Mealy machines, and I've done that on purpose. I've left it till now. I'm going to look at how you convert from a Moore to a Mealy and what it actually means when you implement one. And like we did last week, we can often look for redundant states. It's exactly the same process, pretty much. Okay, so this is the generic Moore machine, and I've shown this slide many times. The storage devices are here. The two D-type flip-flops, and they hold the state. These only change with the edge of a clock, so they're synchronous. The outputs are just a function of state. Now that's really important to remember that with a Moore machine. Okay, this is what you've seen already. The next state is determined by where we are, which state we're in, and the inputs. In this case, there's only one input. So critical, the output's purely a function of state for a Moore machine. For a Mealy machine, I've added this extra wire. And what this does, it essentially says that the output is a function of the state and the inputs. So if I change an input in a given state, I might see a change in the output. That might seem a bit odd. Now we are making an assumption here. We're assuming that the inputs don't change at inopportune moments. So I'm going to assume that you've done some extra work to make sure your inputs are synchronous. In other words, they are stable before and after the clock. Let's carry on. So the key thing is that the output is a function of state and inputs. Okay, and that might seem strange because we're not used to that. Okay, and there are things you can do which we can't talk about now. So I want to look at an example first, and this is the Moore machine, the one we recognize. And this is not the most efficient way of doing this, I would add, but it's a good one because we can understand it. Oops. It's designed to detect a sequence of a 1, a 0, and a 1 on the input. So if we reset into state A, the output is 0. If we get a 1, we go to B. If we get a 0, we go to C. And if we get another 1, we go to D, where the output is a 1. So this is the state, this is the input, this is the next state we go to, which appears on the next clock edge up here. And so we see a 1 in the output when we get a 1, 0, 1 sequence. Okay. If we get a different sequence, say 1, 1, 1, it stays in state B. 0, 0, we'll go back to A. So as long as there's a 1, 0, 1 in there, it'll pick it up. So 1, 1, 1, 0, 1. So the last 3 digits are 1, 0, 1. It will still detect it and give you a 1 in the output. If it goes 1, 0, 1, 0, 1, 0, 1, it'll get that. So it's 1, 0, 1. Another 1 would take us to here, 0, 1. So it's comprehensive. It catches all of them. So wherever they're hidden in the input stream, no matter what state you're in, if you get the sequence 1, 0, 1, you'll end up in state D. Okay. It's just as easy to do it with a shift register and a few gates, actually, but it's an example we can work with. So, excuse me, we have the entity for a device for detecting this. I've called it a 101. It's got a clock input, an asynchronous reset, and an output. Okay, the architecture, we'll look at a bit of it now. Now, I've used a little trick in VHDL. It's really nice because we never actually access the state itself from outside. It's an internal variable telling us where we are, which circle we're in. We can create a new type called state type, and its valid values are A, B, C, and D. So I can create a signal state of that type. So state can be assigned to A, B, C, or D. And this makes the VHDL easy to read. How do they ultimately get represented? Probably as some binary encoding on D-type flip-flops. But we don't have to care. We're abstracted away from the hardware. We're writing behavioral VHDL. So I know this is a bit long, but let's see if we can get through it. So the process block has a sensitivity list with the clock and a reset. Now the Moore machine has, in this case, two process blocks, as you'll see. One for next state and one for the outputs. So this is concerning the next state logic. So this is the asynchronous bit. So without any reference to the clock at all, if the reset is a 0, state is set to A. And I suppose I should set the output to 0 as well. If the reset is not low, then we consider the clock. So if you've got the rising edge of a clock, then we're interested. Okay, so we might change state now. So we look at the state we're in using this case statement. So case, when, and case. So case state is, okay, now when A, run this. When B, it's this. When C, it's this. And when D, it's this. So depending what state you're in as to what set of logic you apply. So in state A, when the input is a 1, the state becomes B. Okay, and that will only happen on the next clock edge, as you'll see in a minute. It'll only affect the output on the next clock edge. Otherwise, it stays in state A. So let's go back to this. So at A, if you've got a 0, you stay in state A. Otherwise, you go to B. All right, so a 1 input takes you to B. And that's what we're saying here. If the input is a 1, the state becomes B. Otherwise, stay where you are. And then it quits to the end of the case and out. If you're in state B, then we look at a different set of rules. So we look at if the input's 1, stay in state B. Otherwise, we go to state C when the input is 0. And we'll see that. In state B, if the input's a 1, stay where you are. If it's a 0, we're in C. In C, it's similar. I suppose the interesting bit is this one. When you're in state C and the input's a 1, that takes us to that last state D. Otherwise, we go all the way back to A. And in D, if the input's a 1, we go back to B. Otherwise, we go back to C. Now, all I'm doing here on each clock edge is updating the state. Okay, remember it's on each clock edge. It doesn't happen before or after. It's on the rising edge of the clock. With the exception of the asynchronous reset, that's all we're doing. So if we get a rising edge of a clock, we look at the state we're in, we look at the inputs and choose the next state. All right, and it's this A, B, C, D. And there's no reference to output signals here at all. It's purely maintaining an internal note of where we are based on what state we're in, what the inputs are, as to where we're going to go next. Okay, now in parallel with that, remember all process blocks, they execute in 0 time. They are just a piece of concurrent hardware. We have the output logic. And this runs in parallel. So when we see the state change, we look at it. Okay, when in state A, output is 0. When in state B, output is 0, etc. Only when in state D, the output are 1. And that's what we've got back here. In A, we've got a 0, B, a 0, C, a 0, D, a 1. It's exactly the same design pattern for every Moore machine. You can just extend this by adding more states. All right, no more complexity. So it scales very nicely in that respect. And I've run a little simulation here. This has come out of Model Sim. I've got a clock, an input, an output, and a reset. Pull the reset high. We've got to look at the clock edge. That's a 0, 1, 0, 1, and there's your output 1. So it's detected it. All right, so that's the VHDL implementation of a Moore machine. So it's nice the way it partitions. You've got a process block for the state transition and a process block for the outputs. And remember, they're concurrent. Right? They're parallel bits of hardware, if you like. Okay, let's move on. So we looked at this last week. A nice way to define this is with a state transition table, where we write what state we're in. For the inputs, 0 or 1, we say what the next state is. And then for each state, we write the output. So this table conveys the same information as this diagram. Okay, so we did that last week. If you can use these slides to come back to this so that you can pick up the format, because it's going to help in a minute. If you draw them like this. Okay, so for each state there is a unique output. So we've got this output column here. That's different with the Mealy machine. Right, so before I actually show you a Mealy machine, I'm going to show you how trivially easy it is to convert a Moore machine to a Mealy. So the first thing we note is what the output is for each state in the Moore machine. So we take a note of that. A, B, and C are zeros, and D has an output of 1. Now keep that in mind. Now we write the state transition table for the Mealy machine. Now let me explain. It's almost exactly the same. So this section here is almost identical. In fact, you could just copy it across, and we delete the output column. Now, what you then do is, for each state, we define the output given the input. So A is a 0. Notice here, we look it up. In fact, it's simple way. Only D has a 1. So A, B, C, B, A. Oh, there's a D, so that has a 1. And the other's a 0. So in other words, you just copy this bit of the state machine, drop the output, and then you, for each of these next states, you also write the output that would have been had you gone to those states, which is this. Okay, so there's the D. D's are 1s, so /1. That's for the next state. That is the state transition diagram for the Mealy machine. What does it look like? It looks like this. Now note, the states no longer have fixed outputs. The output is a function of the state you're in and the input. So input/output. So in your state A, with the input of 0, we get a 0 in the output. In state A, with an input of 1, we go to state B, and we get an output of 0. Similar for B, if you're in state B, input of 1, next state is B still, the outputs are 0. So the actual state transitions at the moment are identical. All we've done is put the outputs here. So if you're in state A and an input of 1 is applied before the clock edge, you would see a 0 appear in the output. More interesting is this one, state C. If you apply an input of 0, you see a 0 in the output. If you apply an input of 1, you see a 1 in the output. And then we'll go to the next state as well. Now that might seem a bit confusing because you're probably not used to it. And there's the table that goes with it. I'll show you the VHDL in a minute to try and add some kind of physical meaning to this. But the main thing we need to, well, often the goal with converting to a Mealy machine is that we can sometimes get rid of additional states. Now I've got one example which I haven't written up yet, but I've left for you as a challenge in a minute, where you can shrink 5 states down to 2. But we'll come to that later. So let's look at state minimization. Now it's no different really. If you've got a state with the same outputs for the same inputs and the same next states, they're the same. All right, they must be. So let's actually look at that. So let's look at this Mealy machine state transition table. No output column here because the outputs are embedded in here now. And that's what makes it possible to sometimes reduce them further. So the S just means self. All right, so 2 selves are equivalent, as we discussed last week. So A goes to A with a 0 input, and to B with a 1 input, etc. Now there are actually 2 equivalent states. And what do I mean by that? Well, the next states are exactly the same. They're 2 C's and 2 B's, and critically, the outputs are the same as well. If you see that, you can get rid of one. And I'm going to get rid of D. And wherever I see a D, I replace it with its equivalent, which is B. So that D there became a B here, and we struck out D. And we're down to 3 states. All right, and that in this case is as far as you can go. Don't be fooled into thinking A, B, B, they're the same. No, the outputs are different. They're not equivalent. All right. So pretty much that's all. Now the last thing to really talk about is, well, what does that mean? Well, here's our reduced state machine here. We're down to 3 states now. I've saved 1. We are assuming that, as I said, the input is synchronous for this to behave in a predictable way, and that when we assign an output, it's latched. Okay, or it's held on flip-flop. So now we only have 1 process block. Clock and reset again as our sensitivity list. Setting the state to A at the start. Strictly, I should have set the output as well. Okay, so we look at the rising edge of the clock and we consider the state. So when we're in state A, if the inputs are 1, then set the next state to B and the output to 0 immediately. Okay, and that's the big difference. We also assign the outputs according to that or that. Okay, so if we look at state B here, if we see an input of no, let's look at C. That's more interesting. If we see an input of 0, we go back to A with it and set the output to 0 immediately. If we see an input of 1, we set the output to 1 immediately and the state to B on the next clock. So here's state C. If the input is a 1, the state goes back to B and we set the output immediately to a 1. Well, at the end of the process block anyway. If the state, otherwise, if the inputs are 0, we go all the way back to A and the output is set to 0. So just by converting more to Mealy, I've saved 1 state, and sometimes you save more because they actually minimize more readily. So I've got this in Quartus as a alternative architecture. I've just got to sort out the test bench with that one, and then I will upload it so you can actually see this and see the timing diagrams and not just believe me. You can see they are actually equivalent. So this is the 101 detector. All right, and that's about it. Now, there's something I'd like you to have a go at if you've got the time. It's a little challenge, if you like. I got this idea actually from my car. Right. So something I noticed with that car, it's got lots of cleverness about it, actually. It's common to many cars these days. So on one of them is the light switches. So I've only included 2 variables here, whereas my car seems to use 3. But take a simplified version of what it does. It's very good at knowing when something's intentional. So if I'm sitting in the car and the engine's off, and I turn the lights on just to maybe park up to let people, so they don't crash into my car park. I can open the door, I can go out, I can shut the door, and no alarms go off because it thinks that, well, the engine's off, you're parked up, and you just turn on the lights. That's an intentional act, so I'm not going to warn you because you know you've done it. And it's right, actually. That is usually what I'm doing. So there's no warning. The warning comes is when your engine's running and your lights are on, and then you shut off the engine while the lights are still on. It thinks you forgot to turn off the lights, and so it makes a beeping noise. It issues a warning. All right. Now, I can write that exhaustively as a 5-state Moore machine, and I will. Maybe I'll scan and upload my sketch of what that is just to get you started. I'll do that in a minute. But for start, I've reduced this to a problem with just 2 inputs. We're keeping doors out of this because doors opening and closing actually get involved. All right, so there's the ignition, which is on or off, and the lights. And remember, just having the ignition off and the lights on isn't enough to set off the alarm. It depends on the sequence. So if I start the engine, turn on the lights, turn off the engine, that will make an alarm. If I don't turn on the engine and I turn on the lights and turn them off, I get no alarms. Yeah, so the sequence is important. All right, so the 2 inputs are there. I've got one output, which is the warning. And these are the things you'll need to do. So you need to draw yourself a state diagram. I say, for now, start with the Moore machine. Write down the state transition table. And looking at last week's lectures, try and reduce the states as far as you can go. Now, when I did it, using an exhaustive approach, I ended up with 5 states, and I managed to reduce that down. I can't remember whether it was to 4. I think it was down to 4. Then I converted it to a Mealy machine, and I managed to reduce 2 more states down to 2, which seems remarkable. So I've managed to get this down to 2, which I never thought I would, actually. I'm going to go through the full solution, or my solution. You may have a different one, but I'd be interested to see what you come up with. So coming up next, what happens when state machines get too big and too complex, which they quickly do, more than a couple inputs, and they get a bit cumbersome, really, or they've got lots and lots of states. How do we break them apart? And actually, sometimes things partition nicely into what we call linked state machines. A good example of that is if, for example, you want a timer. A timer is just lots and lots of states. So you've got one state machine might start a timer, and then the output of that timer is fed back into the first one to say finished. And that's a good example where you can have quite complex user interactions, like holding down buttons to make things happen, etc. All right, so we'll look a little bit at that next time. I think Phil's got the lecture slot next week, which will be on campus. I'll see you in the lab, but we'll do another lecture in 2 weeks' time.